So about analog, I don't know. So I think all of you for your batch on 14th and 15th, I think full days will be there. So class will be from 2 to 8:30. So please note down this. 14, 15, 14th, 15th this month. Class will be from 2 to 8:30 p.m. will be there. Please note down all of you this. That's why only due to Dasara only it is. Yes, because of festival only full days. Okay. Tomorrow as usual, same 5:30 to 9:30. Okay. So you will get in OTS schedule also. Check it is. Tomorrow same class, same time. Yes. Okay. So previously we have seen compound machine is mainly two types, cumulative differential based on direction of current in field windings. Okay. Now second, this is the first category. Now let's see the second category. This is based on compounding. Based on compounding of field windings. There are three types. Write the side heading. Based on, this is first. Now second category is based on compounding of field windings. Because two field windings we have, shunt and series. How we compound, how we mix the two windings, which field MMF is greater, like that. Based on compounding of field windings, there are three types. Actually, it is for cumulative compound. There are three types. There are three are. One is over compound DC machine. Over compound DC machine. Flat compound DC machine. And under compound DC machine. Under compound DC machine. Okay. These three types. Now, how can we get over compound, flat compound, and under compound? Let's see that. Over compound means there are two field windings, shunt and series, 5SH, 5S. How we design these two? Based on that, this is compounding. Over compound means in the over compound, we will adjust the series flux such that it is higher value compared to shunt flux. We will adjust the series field higher. Series field. How we adjust, I will show you in the characteristics, but not right now. In the characteristics. So while drawing characteristics, I will show you how we will adjust that. Okay. 5SC greater than 5SH. That is called over compound DC machine. Flat means almost both fields we adjust, they are equal. Flat. And in under compound, series flux is less than shunt flux. See, in all these cases, shunt flux we keep constant. We don't change shunt. Only series MMF we will change by connecting a diverter. Suppose it is a compound machine. It is a compound. So I'm taking short shunt. It is a compound machine. this is the field current ISH. So flux phi SH is same because ISH will not change. Across the series field, we will put one diverter here, rheostat. By adjusting the value of diverter, this MMF will change because the current in this winding will change when you change the RD here. When this current is changing, your series flux also will change. So based on that adjustment of RD value, we will get the three types. So how we adjust it is, I will show you clearly in the characteristics. Okay, just remember here. In case of over compound, you will get the full load voltage greater than no load voltage. Full load voltage is greater than no load voltage in over compound. In flat compound, full load voltage equals to no load voltage. Under compound, full load voltage less than no load voltage. So how we get all these relations, I will show you there in characteristics. Okay, wait up to that. So these are the three types based on compounding of field windings. How we compounded, mixed, how we mixed. Next, third category in this. Third category. Third sided in based on how we connected the field windings with armature, short shunt connected or long shunt connected. So there are two types based on type of connection of field windings with respect to armature. How we connected that field winding to the armature based on the two connections we have. One is long shunt connection, and second, short shunt connection. Long shunt means shunt looks long. Yes, based on the physical appearance, how it is visible for us. Based on the physical appearance only, we call long and short it is. Long means like this. This is the figure for long shunt. The shunt is connected across both armature and series field. The shunt field is connected across both armature and shunt field. This is long shunt. Shunt looks long here. Shunt looks long. That's why long it is. But in short shunt looks short like this. This is the shunt field. And series field here. Okay. This is short shunt. And this is long shunt. Based on the physical appearance only, we given that names. Long shunt, short shunt. But if there is a machine in front of you, how can you identify long shunt, short shunt? Don't say that on the nameplate I observed. Not nameplate. There is a machine, that's it. You have to identify. How can you identify? So then you have to remove that stator cover. Then you have to check inside the field poles how the windings are connected. Then how can you say that long shunt and short shunt? Can you measure at that time? Shunt is long or shunt is short? That is not possible in machine. For that reason, you have to remember 2 points here. Long shunt means, observe here, long shunt means the shunt field is connected across both armature and series field. The shunt field is connected across both armature and series field. That is long shunt connection. But in short shunt field winding is connected directly across armature only. Like that, you have to go through the terminals and you have to check the terminals where it is connected. Otherwise, you cannot say. Only based on figures, you can say that long or short. But direct machine, you cannot say long or short. Okay. Suppose I'm considering long shunt compound generator, RSC, RA, RSH, ISH, IA, IL, load current. Load is connected here. Voltage across load is V. This is EMF induced in generator, EG. Similarly, for short shunt, if you write terminal voltage V, load current IL, same current will flow here, series feed, shunt, armature current, and EMF induced in generator EG. Okay. Now here important is, out of these two, tell me which one is cumulative, which one is differential. Which one is cumulative and which connection is differential? Can we decide cumulative or differential from the connection? Can we decide cumulative or differential from these connections? No way. We cannot decide, because anything may be cumulative, anything may be differential. See, this long shunt connection may be cumulative, may be differential. Both are possible. So we cannot say. Otherwise, if you are saying directly, then we don't have that category there. Directly there itself, you can say long shunt is cumulative, short shunt is differential. We cannot say that. Okay, we cannot say that. So long shunt may be cumulative, may be differential. Like that, short shunt may be cumulative, may be differential. Okay. Now, if you write the KVL equation of both long shunt and short shunt, see the KVL equation, EG equals to terminal voltage V plus drops IA into same current is flowing in both armature and field here, RA plus RSC plus brush drop. And if it is short shunt, the KVL is EG equals to, see here, V plus IARA, but in the field winding IL is flowing, V plus IARA plus ILRSC plus brush drop. This is for EG. Okay, and here it is little variation. Now tell me, out of these two, which connection is the best connection? Long shunt is best performance or short shunt is best performance? Which one will give best performance? Tell me. Long shunt or short shunt? Which connection is the best connection? Long shunt or short shunt? How can we say long or how can we say short? Tell me that. How can you say long? How can you say short? Proof is required, no? Without that, how can we accept it? Oh, how can we say long? How can we say short? Okay, some of you saying long, some of you saying short. Okay, but I don't say this is best directly, because we need a proof. That's why what we do is, we will do one problem first, and based on the output of the problem, we will see which is the best connection. Okay, with proof. Okay, we will see proof first, then we will decide. Okay, let's see that. Write a question. So here 1 point, right, in long shunt, write 1 point in long shunt. The shunt field is connected. The shunt field is connected across both armature and series field winding. Across both armature and series field winding. Series field winding. The shunt field is connected across both armature and series field winding. Short shunt means the shunt field is connected across armature only. The shunt field is connected across armature only. Okay. Let's see one question on this compound generator. Which is best connection? Let's find out. Write the question. This is previous ESE question, conventional question. Read the question. A 220 volt DC compound generator has armature resistance 0.5 ohm, shunt field resistance 50 ohms, series field resistance 0.06 ohms. If the load current is 100 ampere, then find EMF induced for first long shunt connection, second short shunt connection. If it is long shunt connected, how much EMF induced? If it is short shunt connected, how much EMF induced? So calculate that first. Draw the two figures. Again, same figures draw again. First long shunt and short shunt. Draw the figures. So whether it is long shunt or short shunt, load current is same in both cases. What is the load current? Given that the terminal voltage is 220 volts. 220 it is. Terminal voltage is 220. Load current is 100 ampere. Armature resistance 0.5. Series resistance 0.06. Field resistance RSH 50 ohms. Then what is ISH from this? Tell me directly. Because it is parallel, what is the voltage at this point? 220 only, same voltage. So ISH is 220 by RSH. ISH equals to 220 by 50. How much it is? 4.4, no? Yes, 4.4 amperes. ISH 4.4. Now what is IA? IA, sum of these two, IL plus ISH, 104.4. Okay, then EG you can find easily here. Apply KVL, already you have the equation. Using that, EG equals to V 220 plus IA into 104.4 into RA plus RSC. RA 0.5, RSC 0.06. How much it is? Brush drop is not given, so neglect that. What is EG? EG 278.46, right? 278.46. Okay, so take up to 2 digits. Take 2 digits after point. Yes. Next, this is for long shunt. Calculate similarly for short shunt. Next, short shunt. If it is short shunt connected, how much EMF induces? Short shunt. Same, here also data is same. Voltage across load is 220 volts. Load current is 100 ampere. Field resistance 0. How much it is? 0.6. This is armature current. This is field current ISH. RSH is 50 ohms. RA is 0.5 ohm. Now EG we need to calculate this. EG. Observe here. How to find ISH first? Can we use V by RSH directly? No. If we use directly V by RSH, that is wrong because you have to find this voltage here. Let it is Vx. Is Vx equal to 220? No. Current is going in this direction like this. So this voltage equal to, what is the voltage at this point? This is 220. Same point it is extended. 220 it is. Okay, this point voltage 220 volts. Now what is the voltage at this point? Current going in this direction. So Vx equals to 220 plus drop in this resistor. How much current is flowing? 100 amps is flowing. So 100 into 0.06. How much it is? 220. 100 into 0.06 means 226 volts. Vx, our voltage at this node Vx is 226. The voltage at this node is 226. Some people will get doubt here. So 220 minus 100.06 it is. Not minus. Because direction of current is in this direction, going outside. That's why this voltage is output plus drop in this. Okay, not minus. Suppose if this current is coming inside motor case, then you take minus here. Now it is plus 226. What is ISH now? 226 divided by RSH. RSH is 50. What is the current? 4 point. How much it is? 52. Right. 4.52 amperes. Now, if ISH is 4.52, what is IA? Sum of the two currents, 100 plus 4.52. Then this is 104.52 ampere. Apply KVL in this, calculate easy. 220 plus IARA, 104.52 into armature resistance is 0.5 plus ILRSC, current resistance. In the series resistance, current is IL here. IL is 100 into RSC is 0.06. What is the voltage? EG how much? The value of EG 278.26. 278.26. What is the previous voltage? 278.46. Now tell which is the best, short shunt or long shunt? Which is the best connection? Almost both are giving same voltage with a little slight variation. Which is the best connection? Almost both are giving same voltages. Little point variation is there, but not so much variation. Almost same voltage both are. Now, which connection is the best connection? All are best. See here, the best connection is long shunt. Observe, long shunt is the best connection. Why? Because, see the observation. See, in that conventional examination in the one of the year in engineering services, they asked, what is the observations only? What you observed from that output, or whatever the answer you got, what you observed. See, IA of long shunt is less than IA of short shunt. ISH of long shunt is less than ISH of short shunt. Observe here. What is the IA of long shunt? 104.4. What is the IA of short shunt? 104.52. It is little greater or not? Yes. Some current is greater here. What is ISH of short shunt? 4.52. But what is ISH of long shunt? Only 4.4. So currents are less or not? Yes. So in long shunt, the currents is less in the windings. Whenever current is less, what is the I square R loss in that? Less. Because resistance is same in both cases, but only currents are different. Therefore, efficiency of long shunt is greater than efficiency of short shunt. So which is the best connection in performance? Long shunt is the best connection. Long shunt is best. Okay. Now clear all of you? Winding anything, any both are same only, because just we are joining, no, that is long shunt or short shunt. That is not a problem. Performance wise, long shunt will give more efficiency when compared to short shunt. Okay, clear now? Right. See, in both connections, we got almost same voltage. So there is no big difference in voltage. Neglect that difference. But mainly, if you consider currents in long shunt and short shunt, observe the currents. In which connection current is little greater? Short shunt, 104.52, and field current ISH is 4.52. Whenever currents are more, what is I square R loss in that? More. If I square R is more, what is the losses is more? Then what is the efficiency? Efficiency of long shunt is more than efficiency of short shunt because of more losses in short shunt. Okay. Okay. So with this, our types of DC machine is over. Construction and types over. Now we will go to the next, armature reaction. No complex. If you get any question on this compound, you will get questions on KVL, that is a calculation of EG. That's it. So short shunt, it is important because most of the people will take here ISH equal to same V by RSH, but not V by RSH. This Vx you have to find separately. Okay, take care of this. And sometimes they give in the question brush drop also. Then you have to take brush drop also. Okay. That we will see again where we use this. In long shunt, the shunt field is connected across both armature and series field. In short shunt, the shunt is connected only across armature terminals. Okay. See, sometimes in the questions they give total brush drop. So you take total brush drop. Otherwise, if they don't give, they said that only brush drop is 0.5 volts or 1 volt per brush. Suppose brush drop given 1 volt per brush. Then total how much brush drop you have to take? If nothing is mentioned, because we have to, it has to mention that lap connected or wave connected. Based on that, brushes will change. And poles also they should give. But in some of the questions, they don't give poles, they don't give lap or wave connectivities. At that time, if they given brush drop is 1 volt per brush, then you take 2 brushes, 2 into 1. That's it. That is the total brush drop. If nothing is mentioned. Otherwise, if they given particularly per drop, brush drop per brush is 1 volt and there are 4 pole lap connected, then you have to take 4 into 1. Okay. Right. Next. Next one is armature reaction. So I think very well you know about armature reaction from synchronous generator. Same here, conceptually armature reaction of DC generator or synchronous generator, everything same. So armature reaction between fields. It is the reaction between fields. Every generator or motor will have two fields. Every generator and motor, two fields will be there. What are the two fields we call? One is main flux, another one is armature flux. These two fields will be there. In case of DC generator, where is the armature flux? Where is the armature flux in DC generators? Armature flux is in rotor. Main flux is in stator. But in case of synchronous generator, where is the armature flux? Stator. Main flux is in rotor. Just it is nothing but where you are placing field winding, where you are placing armature winding. That's it. So in synchronous generator, where we use armature winding, stator, 3 phases, and field winding we place on rotor. Field winding will produce main flux. Armature winding will produce armature flux when there is armature current. Now, which is important for us? Main flux or armature flux? Main flux only important for us. We don't want armature flux. Means whenever there is a load, due to the armature current, this armature flux is producing at that time. Now, the effect of armature flux on main flux we call armature reaction. The effect of armature flux on main flux we call armature reaction. But we should never say reverse. We should never say reverse. The effect of main flux on armature is wrong. Main flux will never react with armature flux. Armature flux only will react with main flux. Okay, that is called armature reaction. The effect of armature flux on main flux is called armature reaction. Now, what is the difference between DC generator reaction and synchronous generator reaction? Yes, there is a big difference here. What is the difference is, in synchronous generator, the armature reaction will change whenever load changes. So there you have seen like lagging power factor. What is the reaction? Inductive load, pure inductive load, pure capacitive load, pure resistive load, lagging power factor, leading power factor. If there is load variation, your armature reaction also changes. But in DC generator, is there load variation? What is the load on DC we connect? Resistive loads. So we don't talk about load power factor here. We don't talk about load power factor. So it is independent of load power factor. But synchronous generator depends on load power factor only. That is the main difference between these two. And analysis of armature reaction of synchronous generator is very easy. But DC generator is difficult. Why there it is easy is, in synchronous generator case, we can draw phasor diagram for different load variation. But here we cannot draw any phasor diagram. So directly we have to consider one machine diagram. From the machine diagram itself, we have to see how the reaction is taking place and what is happening in this. Okay. Write the definition of this first. Write the definition. The effect of armature flux. The effect of armature flux the effect of armature flux on main flux is called armature reaction. Armature reaction. The effect of armature flux on main flux is called armature reaction. Make a note here. In DC generators, the effects of armature reaction, are independent of load. Independent of load power factor. Independent of load power factor. So only one load. So we no need to talk about different load power factor here. So it is independent of load power factor. But synchronous generator depends on load power factor only. Okay. Remember this point. Now, what are the effects of armature reaction in DC? There are mainly two effects here. One is demagnetizing effect and second is cross magnetizing effect. But in synchronous generator, one more effect will come. What is that? Magnetizing effect. That depends on capacitive loads. If there is a capacitive load, additional magnetizing effect will take place. But here, only two effects will be there always: cross magnetize and demagnetize. Okay, right? That in DC machines, there are mainly two effects. There are mainly two effects. That is, first, demagnetizing effect. Demagnetizing effect. Demagnetize, in the name itself, what it will do? Demagnetize means it will reduce the flux, resultant flux in generator, or main flux only, that is. Because of that, the flux in generator or motor will reduce. So what happens when flux reduce in generator? EMF reduces. Generator case. If it is motor, which one will reduce in motor? Torque. Torque in motor always proportional to flux. When flux reduces, torque in motor also reduces. Okay. So these are the problems of demagnetizing effect. EMF reduce in generator, torque reduces in motor. Next, one more effect is cross magnetizing effect. Cross magnetizing effect. Now, what is the problem of cross magnetizing effect? The main problem of cross magnetizing is distortion. So how it will take place, we observe. Distortion, which causes mainly spark at brushes. The reason, so previously I said in the construction part. So what is the reasons for spark at brush? Two reasons: constructional reason, operational reason. So this is only the operational reason. Whenever it is supplying some load, there is a cross magnetizing effect which causes spark at brushes. So this is one problem of cross magnetizing effect. Okay. The spark is dangerous thing. Whenever we don't reduce the spark at brush position, it will damage entire machine also. So spark, as much as possible, we need to control the sparks. Okay, you cannot eliminate completely. Anyhow, spark will come, but we should limit that. Okay, so these are the main two effects in DC machines. Now let's see how these two effects taking place in the DC machines. So for this, you need to draw some figures here. Just wait for some time. Okay, see this. So draw same as it is. This is same figure 3 times. Draw the same figure in your book 3 times. Same figure. Total 3 figures you have to draw. Same as it is, 3 figures. So why 3 figures is, in the first figure we will consider only main flux. If there is only main flux, what is the path of that? And in the second figure we will consider only armature flux. And in the third figure we will consider both. In the third figure, both armature flux and main flux, phi A and phi A, both we will consider in this. That is resultant. What is the effect of armature flux on main flux? How we get resultant flux, that we will draw in this. Okay, so take same as it is, 3 figures. Now there are some important axes here, names. See this. See, there are two axes in every machine. Every machine, synchronous or DC, anywhere, there are mainly two axes. One is D axis, another one is Q axis. So the axis passing through the poles, let it is north, south. The axis passing through the poles we called D axis, also called polar axis. The axis passing through the poles we call polar axis or D axis. And what is the other axis here? This is Q axis. The axis perpendicular to D axis we call quadrature, perpendicular, electrically perpendicular Q axis. This is also called interpolar axis. Interpolar because this axis will pass exactly in between the two poles. That is interpolar. It is also called GNA, geometrical neutral axis. It is also called MNA, magnetic neutral axis. It is also called brush axis. It is also called axis of commutation. Axis of commutation. So these are all names for Q axis. These are all names for Q axis. First, draw the figures. Armature reaction in both generators and motors, not only generator. Okay. See, did you observe in previous synchronous machine or not? Is armature reaction only in generator, only in alternator? Simultaneously, we see motor also there. In motor, if it is a demagnetization in alternator, in motor case for same power factor, it is magnetization. So did you think one important observation at that time? Alternator operating at lagging power factor, pure inductive load, for example, purely inductive load. What is the armature reaction? Demagnetization. Synchronous motor operating at same inductive load. What is the armature reaction? Magnetization, opposite. So here you should get one doubt first. Any doubt there? Did you got any doubt at that time? Okay, you don't get. So the doubt will come should rise is synchronous motor. What is the load on motor? Mechanical or electrical? Load on motor is what? Mechanical. Then how can you consider inductive load, capacitive load? This is wrong or not? Synchronous motor load is mechanical. Then how can you say inductive load, it is operating capacitive load? So that is not supplying inductive load, but the nature of the motor behavior is inductive. Nature of behavior of motor. Power factor, it is operating at ZPF lag or ZPF lead. So synchronous motor can operate at any power factor. By changing excitation of the motor, it can change power factor, but it won't supply inductive loads or it won't supply capacitive loads. Okay. Yes, right. Okay, observe here. First, let's write what is the definition of this axis. First, write polar axis. Starting polar axis. What is the polar axis? Yes, in the name itself. The axis passing through the poles. The axis passing through the poles. Through the poles is called polar axis. This is also called direct axis, D axis. Okay, next. The axis passing through the poles is called polar axis or D axis. Next one, GNA, geometrical neutral axis. Geometrical neutral axis. So it is nothing but geometrically or physically neutral, which divides the machine exactly the center of poles. That is, it will divide the two poles into exactly two halves. Individually, it will divide north pole separate, south pole separate. That is the axis, right? The axis which is passing in between the poles, is called geometrical neutral axis, GN. Okay, GNA is fixed one always, it never change. But there is MNA, that is dangerous. MNA will change. So the questions also important on that. So MNA will shift in which direction? Generator direction or motor direction? So right, next MNA. Next one, MNA, magnetic neutral axis. MNA, nothing but magnetic neutral axis. So already you know what is MNA. What is MNA? Previously we have seen first class. The axis where EMF induced is zero, or the axis where there is no effect of north pole, no effect of south pole. Neutral point, that is called neutral axis. So that is one definition. There is another definition for this MNA. So both we write here, observe. Magnetic neutral axis. Magnetic neutral axis. See, the axis where there is no effect of north pole, there is no effect of north pole or south pole. North pole or south pole. Okay, that is wherever EMF zero, that is the neutral axis. This is one point, one definition, and another definition is, or the axis which is always perpendicular to resultant flux in the machine. Resultant flux of the machine. Resultant flux of the machine. So I will show you all these points in the figure now. Where is the resultant flux, where it is perpendicular and all, we will see now. The axis which is always perpendicular to resultant flux of the machine, that is also called MNA. Now make a note here. See, no load case, no load means generator is not supplying any load, open circuit. At that time, MNA, GNA both are same. Both are in same axis. But whenever load connected, MNA will shift from GN. So in which direction it will shift, that we have to observe. Right here, under no load, MNA is in phase with GNA. MNA is in phase with GNA. But under load, the MNA will shift from GNA. The MNA will shift from GNA. The MNA will shift from GNA. So in which direction it will shift, that we will write again after completion of the figures. Okay. Now come back to the same figures. Come back to the previous diagrams. Observe here, one by one we draw the figures now, 3 figures. First figure is simple, only main flux. Main flux means whatever these poles will create, that is our main flux by excitation. Field winding is there here. Okay, by giving that separately excited or self excited, whatever the flux is passing north to south pole, this is main flux direction. This is the main flux. So main flux lines are passing north to south like this. Okay, north to south. Now all these flux lines I will indicate as a single line like this. So this is the main flux. Main flux is passing in this direction. All the flux lines I am indicating a single line. Okay, so below that draw this line. First figure is easy, and in this the second figure is the most important. Now observe this. Second figure only armature flux. So this is our q axis, this is d axis. See here, considering it is a generator. Generator means we have to rotate by prime mover at a speed n. We need to rotate, generator means. Now, as a generator, we are rotating clockwise. There is north and south here. Poles are there. Main flux is passing in this direction, but we are not indicating that. Only armature flux we indicate in this. Only armature flux. See, main flux is there, but not drawing. Okay, but not drawing, that is in this direction. And rotation is in clockwise. Rotation of the rotor is in clockwise. Now some EMF will induce and current will flow because load is connected. What is the direction of current? How to find direction of current? What is the motion of conductors? Upward, 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 because when you rotate clockwise, this conductors is moving in this direction. This is the motion of conductors I am drawing at every conductor, how they are moving, motion. So when you rotate clockwise, the conductors are moving like this. Under north pole, motion is upward direction. Under south pole, motion is always downward direction. Okay? Motion is always downward direction. Clear? Just motion I marked. When I rotate clockwise, motion I marked. Now let us apply Fleming's right hand rule. Apply Fleming's right hand rule. Four finger flux direction. Main flux is there, north to south. So that is our four finger. Motion is, thumb indicates motion of conductor. Now middle finger indicates current direction. So by applying Fleming's right hand rule, so I am getting current direction cross, 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 because motion upward only. From here motion is downward. That's why you change your finger upward to downward like this. Then what is the middle finger? Coming outside. Outside means here dot will come. Dots. Dot, dot, dot. So is this clear for all? As a generator, we are rotating clockwise. As a generator, we are rotating clockwise. Direction of current clear for all? By applying Fleming's right hand rule, we are marking current direction. Clear now it is, all of you. Okay. Now observe. Let us assume armature I am rotating clockwise with a prime mover clockwise direction continuously at a speed n rpm. Now you keep on observe the armature only, how the currents looks like in that armature rotating. Even armature rotating, what is the direction of current under north pole? Always cross only. What is the direction of current under south pole? Dots only appears. Dots only appears because motion is always down. Conductors rotating, even they are rotating, current direction under north pole is cross. Under south pole is dot. They never change again. That's why. So according to this dotted line, this is dividing the armature exactly two halves. This dotted line. With respect to that, you apply right hand thumb rule there directly. Apply right hand thumb rule. In the armature, apply right hand thumb rule. So four fingers going inside under north pole, coming outside under south pole. Then your flux is downward direction. That is armature flux is downward direction. If I apply right hand thumb rule here, I am getting the flux direction downward direction. This is armature flux. Means there is a pole here. What is the pole here? Tell me. This is a south pole or north pole? Here also there is a pole formation. What is the pole formation here? South. And this is north. Why? Flux is south to north inside. Externally north to south. Externally north to south. Okay. This is clear for all. See, field means north and south. Whatever the flux is produced by the poles here, that is field, main flux. And this is our armature flux due to armature current. So clear now up to this? Clear? Now I will show you in the first class, I think, okay, how I applied right hand thumb rule. See, I cannot show you here. Mm, see, in your book only, after drawing this current indication, apply in your book itself, right hand thumb rule. In the armature, one half of the armature cross. One half of the armature cross means what is the four fingers? Current direction. What is the thumb indicates in thumb? Right hand thumb rule. Thumb indicates flux. If four fingers is current, thumb indicates flux. So cross under north pole. Cross means it should go inside your book and comes outside. Okay, right hand thumb rule I am applying. Going inside, coming outside. Fingers. Curl, however, the curl, four fingers. Apply the current and thumb indicates flux direction. That's why I marked armature flux is in downward direction. Clear it is now? Apply in your book itself, right hand thumb rule, in the armature. You will get the flux direction in that. So flux is coming in this direction means south is here, north is here. Okay, clear now? It is south pole, north pole, armature flux, how it is produced. Top portion is not north because see in a magnet north south. Tell me what is the flux direction in magnet inside? Inside south to north, outside north to south. That is only a mark. Inside south to north. Inside na it is. That's why I taken south and north. Outside north to south. After this, I will draw that completely. I'm not drawing right now. I will draw it. Okay. Inside na south to north. Clear now? What is reverse in the construction? Tell me. Now clear all of you internally how south and north it is. All of you. Flux always pass from north to south, but where north to south? In the air. Inside south to north. Clear now? Okay, observe here. Now only important points. In the starting class, I given in the basics. Already you know that points also. What is that? In a generator, torque will produce. What is the direction of torque in generator? Opposite direction of rotation. Okay, next second point. In a motor, torque will produce. What is the direction of torque? Same direction of rotation. So whatever the direction torque is produced, in the same direction motor rotates. But in generator, the torque produced is always in opposite direction. So that proof I am showing here. Observe how it is. See, as a generator, which direction you are rotating? Clockwise. But observe, whenever armature is rotating continuously, south and north looks stationary or not? Tell me this point first. The south and north in the armature located at the same place or not? South and north located at the same place. Why? Even armature rotating, currents are same only. That's why south always here, north always here. Okay, that position is not changing. That's why now what this south pole will do here? This south pole is attracting towards north pole, opposite pole. This north pole is attracting towards south pole. Attracting, that is nothing but electromagnetic torque. That is only torque here, that attractive force. That is nothing but magnetic drag in generators. This is nothing but magnetic drag in generators. In every generator, it will be there. Synchronous also, it will be there. When you rotate clockwise, internally some torque is producing. That torque is trying to drag the rotor, but it won't rotate, just dragging. That's it. That is opposition. So in a generator, the torque produced is always in opposite direction of rotation. Clear now? Why it is opposite? Because south attracting towards north, this north pole attracting towards south. So clear all of you this point? How generator torque is opposite direction? Yes, that is nothing but motor action in generator. Clear now it is. Now, if it is motor, which direction it rotate? Motor means what? Motor means you should remove this prime mover. Motor means you should not give any mechanical input. What you have to give for motor? Current. Assume that same current we are supplying for motor, same current. Then in which direction torque produce? Same direction. If it is cross and dot, south here, north here. South attracted towards north. So if it is a motor, in the same direction it rotates. If it is a motor, in the direction of torque it rotates. Now how DC motor is self-start? That is also I will show you here. How DC motor is self-start or not? Yes, self-start. How it is self-start is observe. Once you give supply to the motor, cross here, dot here. That cross and dot will never change. Always cross under north, always cross dot under south. They never changes. That's why south is here, north is here. Armature poles. South attracted to north. North attracted to south. So twisted. Rotor is twisted now. Whenever rotor is twisted, is south and north will come here? Is this south and north will come here? No, they don't come. If they come, they will lock. No, they cannot rotate. They don't come because current under north pole is always cross only. Current under south pole is always dot only. That's why this south pole, this north pole will never move from that position. They are at the same position. That's why continuously there is a torque acting or not. Yes, this is called unidirectional torque. Due to that, rotor continuously twisted, rotated. South will not come here. If south come, attracted and stops, but it never come. Why? Because the currents we are maintaining in same direction. In same direction we are maintaining. Okay, now clear how DC motor is self-start. See, have you experienced any time torque of motor? Have you experienced in your life? Never. If you want to experience torque, how much force it is, how much torque, how much force, you just better is there are some motors you can hold in your hand also, the shaft of the motors. Example, drilling machine easily available, workers. So wherever, carpenters or electricians, plumbers, anywhere drilling machines available. So what you can do is take the drilling machine and the shaft of the drilling machine you tightly hold and try to little switch on that drilling machine slowly. You cannot hold that much torque will produce. You use your total energy on that. Still, if you use the total energy, you cannot stop that. Slowly, if you start rotating also, you cannot stop that shaft. It will drag, that much torque will be there. So that you try to directly analyze, means directly have that torque in your hand. How much torque will produce in motor, you will understand. So much force will produce. You cannot stop that shaft. Best example is drilling machine. You take the drilling machine and hold the shaft in your hand tightly and try to switch on slowly. You cannot hold that. Definitely you cannot hold. That much torque will produce in the motors. So like that, it will rotate at high speed in this direction. Unidirectional torque we call it. Okay, now this is clear. In a generator, torque always in opposite direction of rotation, and in a motor, the torque is always in same direction of rotation. Okay, this is clear. Now one question I will give, try to answer this. This is relative speed questions. So these questions are there in induction motors, also synchronous machine, and also now DC machine. Try to answer this question. 100% you will wrong only give. You will give wrong answers only. Okay, try to answer this. Write the question here. So how self-start? So not like that, not more than other machines. We cannot say torque depends on current magnitude and flux produced in that coils, number of turns and all. So torque we cannot compare directly, but we can say series motor in DC will have highest starting torque among all other motors. Okay. See how it is self-start, I said. When we give supply to motor, suppose same current I supplied to motor, then south is forming here, north is forming here. South attracted to north. So rotor twisted, means rotated. Once it rotated, south will not rotate. South is there only, means continuously torque is acting towards this direction. Twisting is in this direction, anti-clockwise direction. So like that, it is a self-start motor. But if you see single phase induction motor, currents will change here. Currents will change there. In case of single phase induction motor, if we give AC supply, no, see one half here positive, other half here negative. So positive, suppose cross dot. What is the torque direction now? Anti-clockwise. So little rotated. Within small time, negative half cycle will come. At that time, currents will interchange. Again, torque will produce in clockwise. So there is a resultant torque becomes zero. It cannot rotate. But DC motor continuously same direction torque will be there. That's why it is a self-start motor. Continuously it rotates in only one direction. Okay, anyhow, I will give first this question. Try to answer this. Interesting question it is. See, question. A DC generator is rotating. DC generator is rotating in clockwise. Is rotating in clockwise by prime mover. A DC generator is rotating in clockwise at a speed capital N RPM. At a speed capital N RPM. Okay, capital N RPM, it is rotating. Next, first question in this. The speed of armature flux, with respect to stator is dash. Second question. The speed of armature flux with respect to rotor is dash. With respect to rotor is dash. Third question. The speed of armature flux is dash. The speed of armature flux is dash. So these are the questions. A DC generator is rotating in clockwise direction at a speed capital N RPM. Now, what is the speed of armature flux with respect to stator? So same as it is questions in induction motor also. What is the speed of stator flux with respect to rotor flux? 0. What is the speed of stator flux with respect to rotor? Ns minus N. So like this type of variations. Same as it is here. So first tell what is answer for first question. Speed of armature flux with respect to stator. Okay, yes, good, very good. Most of you given right, that is 0. This is right. This is right. Second question. Speed of armature flux with respect to rotor, how much? Speed of armature flux with respect to rotor. With respect to rotor. So I'm expecting right answer at least from 1. Yes, there is 1. Speed of armature flux with respect to rotor. Yes, devious rewrite. Okay. The answer for this question is 2n. The answer for this question is 2n. The speed of armature flux with respect to rotor is 2n. If armature generator is rotating at n means it is 2n. Double. Next, what is the last answer? Speed of armature flux is dash. Speed of armature flux. Speed of armature flux. Speed of armature flux. I'm asking, I'm not comparing, I am not asking a reference of this. Armature flux only I'm asking, but not asking reference. Reference I'm not asking with respect to stator, that is over already. Now only armature flux speed is how much? That is minus N. That is minus N. Clear all of you? Is it clear? Okay, definitely not clear. Okay, I can expect it is not at all clear. So you need still clarification of this. Still clarity required. No? Okay, so I will give a good clarity of this to understand. You will get a clarity. Observe here. Observe this. Consider it is a wall. This is a wall, big wall it is. Wall is nothing but stator. Stator will never move stationary, no? That's why taken it is a stator. Wall it is. Now adjacent to this wall, I'm taking a big giant wheel, like giant wheel structure, not giant wheel exactly it is. It is like a giant wheel, but not giant wheel. Like this. So much big rotating wheel it is. So much big rotating wheel it is. Big rotating wheel, and the height of this wheel also so much. Like the height of the wheel is approximately like 20 feet it is. Then only it will work out. Otherwise it cannot. See here. Now a big rotating wheel I adjusted here, and 20 feet wheel, and the wheel width also so much, like 2 feet width is there. You can stand, you can sit, you can sleep on that happily. And I said you go and stand on the wheel. You go and stand on this wheel. Okay, now you are standing on this wheel is still not rotated. Now let us consider this wheel is rotating in clockwise at a speed 10 rpm. Now wheel starts rotating in clockwise direction. Now it starts rotated. Okay, then in order to protect yourself, what you will do? If you don't want to protect, if you stand enough, you will come down with damage. That is, if you are just stationary, if you are just standing on that, definitely you will fall down from there, because if you are not moving. So in order to protect, because 20 feet is there, 20 feet means definitely it will create a problem, damage. That's why in order to protect yourself, what you will do? You will run in opposite direction. At what speed you have to run again? Can you run at a very high speed? No. At what speed? Whatever the speed this wheel is rotating, same speed you have to rotate in opposite direction. Then your position is here itself. You are safe there. Now I think you understand it. What is happening here? This is our stator. This fellow is our armature flux. This wheel is the rotor. Okay. Now see here. What is the speed of armature flux with respect to stator? See, assume that this is U only. What is the speed of U with respect to stator? You are watching the wall and you are running. What is the speed of U with respect to wall? Zero only, because with respect to wall, you are not moving anywhere, there only. So you feel that zero speed. You are there only. With respect to wall, you are there only. That's why the speed of armature flux with respect to stator is zero. Now you observe rotor. Now what is the speed of U? What is the speed of this armature flux with respect to rotor? Rotor is moving in this direction, you are moving in this direction. Now you will observe that relative speed is very high. Now what is the relative speed? Double or not? That is 20 rpm. The speed of that person with respect to that rotating wheel is 20 rpm. Relative speed. Two bodies opposite direction. Okay. What is the speed of armature flux with respect to rotor? 2n, double. Relative speed we are considering. Next, what is the speed of the person? What is the speed of person? 10 rpm. In which direction? Opposite to rotor direction. That is only a given. Armature flux speed is minus n, opposite to rotor. Clear at least now? Is it clear? Not minus 2n. See, with respect to rotor, suppose two bodies, two trains are moving in opposite direction. What is the speed you take? Double or minus 2n? 2n only, double, just relative speed. What is the, if two bodies moving in opposite direction, suppose you are in one train, other train is moving in opposite direction adjacent to you, then what you will feel? Your speed is very high. That's it. That is not 2n or minus 2n here. That is double. That is only a given. 2n is the speed. Speed of flux with respect to rotor is 2n only, not minus 2n. How minus 2n? Who said minus 2n? 2n only, correct. Okay. See, you just observe the rotor. What is the speed of what you feel at the time? Suppose you are observing rotor while running. What you will feel? Very high speed. So that is simply double. Okay, right. Okay. So come back to the armature reaction, how it is taking place. Observe. Now, in the second figure, we need to mark armature flux. In the first figure, main flux is like this. Main flux direction. Main flux direction it is. Now, how armature flux? It is along q axis, coming down now. That's why from this, it is coming down. This is the armature flux. So armature flux indicating with single line. And how to mark that armature flux completely? If you mark here, see this. So I will take in this diagram. So only armature flux. Let us consider only armature flux here. Only armature flux. So when we rotate clockwise as a generator, the direction of current we got cross under north pole, dot under south pole. Okay. Now, according to right hand thumb rule, let us mark the flux direction for each conductor. Suppose this one, cross. Apply right hand thumb is current direction, four fingers is flux direction. If you apply right hand thumb rule here, the flux I am getting clockwise like this. Flux direction I am drawing. This is armature flux. By right hand thumb rule it is. Okay. Armature flux. And under south pole, dot. Dot means current outside. Thumb is outside. Your four fingers will be anti-clockwise. Apply in your figure anti-clockwise by right hand thumb. This is the flux direction. Okay, flux direction. So anyhow, along the q axis, flux is going downward direction. That means here there is a south pole, here there is a north pole. Now it is complete armature flux, north to south, like this flux is flowing continuously. North to south, internally south to north, internally south to north. Okay, so this is the second figure. This is our second figure, only armature flux. Last one, y minus n. Y minus n, y minus n I taken. So what is the question lastly? What is the speed of armature flux? So armature flux only I'm asking. I'm not comparing. What is the speed? 10 rpm. That is whatever the rotor speed is there, same speed it is n. But why minus n? Minus because what is the reference is rotor is our reference because we are rotating in clockwise. So with respect to that, what is the direction of the armature flux? Opposite. That's why minus n taken. Okay. Now third diagram, third one. So there we will consider effect of armature flux on main flux. Let's see how the third one we get. Third one. See the third diagram, both the effect of armature flux on main flux. Both armature flux and main flux are interacted, and how the resultant we get. Resultant. Actually, if you see the first diagram, how the main flux lines are going straightly, north to south, main flux. But here, see how the flux will go. This is generator direction. We are rotating clockwise. Now current direction is cross under north, dot under south. South. Okay. Now resultant flux we need to draw. If you observe the first diagram, where is that first one? This is the main flux. It is coming straightly. When there is no armature flux, no reaction, main flux is coming happily from north to south straightly. It is coming north to south. Okay, clear? But now when there is armature flux, how armature flux? Observe the figure. Actual main flux is coming here in this direction. This is main flux lines. But when there is armature flux in this direction, because of that armature flux, now main flux line will deviate like this or not? Yes. Effect of armature flux on main flux. So we get the resultant is, this is the resultant. Observe. Actual main flux should go straightly, but due to the armature flux, now most of the flux will come towards one pole tip like this. This is the flux direction. This is main flux actually. Main flux is not going straightly now. It is going with distortion. It is distorted. Why it is distorted? Due to armature flux, it is distorted. Clear? How it is going like this? Because of armature flux effect it is. Due to the effect of armature flux, the main flux is distorted. Clear? Actual main flux line it is. Straightly it has to go. But due to armature flux effect on this main flux, it is distorted. Okay? It is distorted. This is GNA. Now where is MNA? This is main flux. This is armature flux. Perpendicular along Q axis. Now resultant of these two means how we get. So approximately this is GNA. This is GNA. GNA will never change along Q axis only. Resultant of these two, if you draw, you will get like this. This is resultant flux. This is resultant. Now what is the MNA definition I said? It is the axis always perpendicular to resultant flux. Now resultant flux means this is resultant. Draw perpendicular to this. Draw perpendicular. This is now MNA. Magnetic neutral axis is this. Now if you draw in figures, this is our MNA. This is, draw approximately, these are the flux lines. Draw perpendicular to that. This is MNA, magnetic neutral axis. Okay, this is MNA, magnetic neutral axis. Which direction it is shifted? In which direction it is shifted? It is generator direction. It is motor direction. Motor direction anti-clockwise. Generator direction clockwise. Okay. So in which direction MNA shifted? MNA shifted from GNA in the direction of generator. So which direction it is shifted? In the direction of generator or opposite to motor? Which direction MNA shifted? Both. You can say in the generator direction or in the opposite direction of motor. Anything correct only. Okay. So MNA shifted. So write that point in the note because this question is important. In which direction MNA shifted due to armature reaction? Which direction? Generator direction. Right. Under load condition, under load due to armature reaction, due to armature reaction, due to armature reaction, the MNA is shifted. The MNA is shifted in the direction of generator. In the direction of generator. Okay. Now observe one more. Due to armature reaction, most of the flux is concentrating at one side only. Okay. Actually, in first diagram, how the main flux distribution from one end to other end? Uniformly flux lines are coming, not one end of the pole to other end of the pole. This is called pole tips. This is one pole tip. This is another pole tip. But due to armature reaction, where most of the flux at one side only, and this pole tip we called here trailing pole tip. Wherever flux density is high, that is the trailing pole tip. And here flux is very less at this tip. This pole tip we called leading pole tip. So what is leading and trailing definition is, observe here. This is called leading tip and this is called trailing tip. Observe. What is leading pole tip is? Observe carefully. Leading means whenever armature is rotating clockwise direction, no, it is clockwise. Whenever armature is rotating in clockwise, every conductor in armature is touching which tip of the north pole? Touching means entering. Here it enters. See, every conductor is entering at this tip. Okay. Every conductor is entering at this pole tip. This pole tip we call lead because every conductor is enters at this pole tip and leaving at this pole tip. This is called trailing. Similarly, under south pole, which is the leading pole tip? This is the leading pole tip. Why? At this pole tip, every conductor enters whenever it rotates. See, suppose example you take any one conductor. Suppose this conductor. This conductor first enters at this pole tip. So leading pole tip it is. And where it is leaving, here it will leave. This is called trailing pole tip. So what is leading pole tip definition? The tip where every conductor in armature enters the north pole or any pole. Enters the pole, that is called leading pole tip. And other pole tip we call trailing pole tip. Wherever it leaves, every conductor will leave this pole tip for north pole. Clear this point? Trailing and leading. So, due to armature reaction, at which pole tip in generator flux concentration is high? Where flux concentration is high? This question is important. In a generator, due to armature reaction, where flux concentration is more? At trailing pole tip. At trailing pole tip, flux concentration is more. And this effect we call Strengt-then effect. Strengt-then means increasing strength of the flux. Strength-then effect of flux. And at the leading pole tip, we have weakening effect. Because what is the magnitude of flux here? Decreases. That is weakening. Strength-then effect at the trailing pole tip. Weakening effect at the leading pole tip. Okay. Let's complete all of this figure. See, there is no end in the machine in any topic. There is no end, it is over. So much is there in the same second figure. So much is there. Like your hunting topic, alternator hunting takes place. How hunting takes place? That is also there in the same diagram. What are the reasons for hunting? Sudden change in the load. Whenever load changes, hunting. Or whenever excitation changes, hunting. Or whenever sudden change in the turbine input, hunting. So these are all there in the same. Okay. See what is trailing pole tip and leading pole tip means. Uh, see the another diagram. Suppose this is armature. This is armature. Now this is one pole. Let it is north pole. It is south pole. Okay. North and south. So for north and south, we are rotating clockwise. Rotor, we are rotating clockwise. Now, where is the trailing tip? Where is the leading tip? Leading means, suppose as you are rotating clockwise now, let us consider one slot. Let us consider this slot. It is started from here. Okay, assume that this is one slot. Now rotor starts rotating. Whenever rotor starts rotating, for south pole, under south pole, this rotor or this slot is entering at this pole tip. So here it enters here, entering here. This is called leading pole tip. Now whenever it is rotating, the same slot will leave this pole tip. So this pole tip we call trailing pole tip. This is for south pole. Next, again after some rotation, this slot will come under the north pole and it will enter at this pole tip. Now this pole tip we call leading pole tip. Now same slot will leave this pole tip after some rotation again. It will leave this pole tip. So this pole tip we call trailing pole tip. So clear what is trailing and what is leading? Wherever at the tip, wherever conductor enters into the pole, that is the leading. Wherever conductors leaves the pole, that is trailing pole tip. Clear now? Okay, brake is required. So don't saturate. Still so much is there in armature reaction. Okay, take break. After break we continue. Take a break. Yes. So in case of motor, leading pole tip will become trailing because motor will rotate in opposite direction. No. So whenever motor rotating anti-clockwise, at that time, see for motor case, so for generator, it is a trailing pole tip. For motor, it will become leading pole tip. So if you get a question in a generator, at which of the following pole tip strength and effect will take place? What is the answer? Trailing. Now, if they ask in case of motor, at which of the following tip strength and effect will take place? Lead. It will change. In case of generator, trailing pole tip strength and effect means flux is more here. And in case of motor, it will become lead. Why? Motor rotates anti-clockwise. So whenever it is rotating in this direction, so every conductor of armature will enter at this pole tip. Now it is a leading pole tip. So same trailing pole tip will become leading for motor case. Okay. Remember for generator, if they ask for motor, say opposite. Trailing will become lead, leading will become trailing. Okay. So how can we say MNA shifting in the direction of generator means actually MNA is previously here. No load condition, GNA, MNA both are same axis. Under no load, GNA, MNA both are same. But when load is connected due to armature reaction, MNA shifted in this direction now. In this direction. Little angle it will shift. Little angle it is shifted. So which direction it is? Generator direction. That's why it is taken generator. Clear now? So what is the MNA definition? It is perpendicular to resultant flux, I said. Now perpendicular to resultant flux means this is only. Now if you consider here MNA shifted, no? That is MNA shift. Okay. See, right here. So what is effects of armature reaction? Two effects, demagnetizing and cross magnetizing. And how we call demagnetize it is, how it is demagnetized is here. Observe this figure. Due to armature reaction, that is effect of armature flux on main flux, most of the flux is concentrating at this pole tip and very less amount of flux at this pole tip. Now previously in first diagram, from this end of the pole tip to another end of the pole tip, flux is uniform. But now due to armature reaction, all flux lines deviated at this pole tip. Due to that, if whatever the flux is becoming strengthened, or if whatever the flux is becoming weakening here, if same amount of flux is strengthened at the other pole tip, there is no demagnetizing effect. But due to more flux density here, this trailing pole tip will saturate because what is the pole tip area? Very small. If little flux lines increases at that area, it will saturate. Trailing pole tip will saturate. So once it saturates, it doesn't allow any flux. It doesn't allow any flux to pass through that. Whenever flux is not coming means the overall flux in the machine will reduce or not? Yes, that is called demagnetize. So why demagnetization? It is due to saturation of pole tip. Because of the saturation of trailing pole tip, the strength and effect is less than weakening effect. What is meaning of that? See, some flux lines are reducing here. Whatever flux lines reduces at the leading pole tip, same amount of flux lines should increase at the trailing pole tip, but not increasing. Why not increasing? Due to saturation of pole tips. So before armature reaction, under the pole, there is 100 flux lines. See, before saturation here, under one pole, 100 flux lines are there. But due to armature reaction here, due to armature reaction, now the total flux under the pole is 96 lines. 4 lines are not there, means resultant flux is reduced. The reason is saturation of the pole tip. This is called demagnetizing effect. Okay, this is demagnetized. Now what is cross magnetize? Cross magnetize. Why cross magnetize is, observe, main flux and armature flux are perpendicular each other. In alternator also, for UPF load, the main flux and armature flux perpendicular to each other. Then that effect we call cross effect or cross magnetizing effect. The corresponding armature flux we call cross flux here, because it is exactly perpendicular to main flux now. That's why it is called cross flux. And the effect we call cross magnetizing effect. Due to that effect only, this flux is distorted. Actually, it is main flux straight line, but now it is distorted due to armature flux. That distortion will cause spark at brush now. So how that spark will come, we will see now in the diagrams. First, write about these two effects. First one, demagnetizing effect. Demagnetizing effect. So how this effect is taking place? Due to saturation of pole tips. Right here. Due to armature reaction, the flux is concentrating. The flux is concentrating at the trailing pole tip. The flux is concentrating at trailing pole tip, which causes saturation of pole tip. Saturation of pole tip. Hence, strengthen effect of flux. Strengthen effect means increasing the magnitude of flux there. Strengthen effect of flux is less than weakening effect. Is less than weakening effect. Whatever flux is weakened, that much is not strengthened because of saturation. Is less than weakening effect of flux. Hence, the flux per pole reduces. The flux per pole reduces, which is called demagnetizing effect of armature reaction. Demagnetizing effect of armature reaction. So what this demagnetizing effect will cause? Flux reducing. Flux reduce means EMF reduce. Some voltage drop due to armature reaction. And if it is motor, torque in motor affected. Torque in motor will reduce as flux is reduced. Okay. Second one, cross magnetizing effect. Second one, cross magnetizing effect. See. During armature reaction, the armature flux is quadrature with main flux, that is perpendicular. Quadrature with main flux, which causes distortion, of main flux. Which is called as cross magnetizing effect of armature reaction. Due to this, there is a spark at brushes. There is a spark at brushes. So how that spark will come, we will see later. Now we have seen the armature reaction with respect to diagrams, machine diagrams directly. So here we have considering only flux lines, how they are passing. But let us consider now the same armature reaction graphically represented. How we can represent graphically? Graphically in the sense, we have to consider linear diagrams. Linearly are called developer diagrams. That is, let us assume that this is a paper. Assume that this is a paper. Assume this is paper. Now cut this is here. Cut the paper here. Now let us take these two ends in your hand, this one and this one. Now expand the two ends. Now it will come in a straight line. Now the figure looks like linearly. That is called developer diagram of this machine or linear representation of machine. Now that is we call graphical representation of armature reaction. So why that is we are considering is in that figures, in that graphical representation, you will get shape of main flux, shape of armature flux, and shape of resultant flux. These shapes important in objective questions. Already you know the shape of main flux. What is that? What is the shape of main flux? Flat top or trapezoidal in the construction of field poles we have seen. Like that shape of armature flux and resultant flux also we can find in that. Okay, but in these diagrams you don't get the shapes. In these diagrams you don't get shape here. Only lines we are drawing, how it is moving, flux lines. Okay, right, starting. Graphical representation of armature reaction. Graphical representation of armature reaction. So start this one in your book at the starting of the page, top of the page. So there only we draw the three signals: main flux, armature flux, resultant flux in the same page. So start this in the fresh page at the top. Graphical representation of armature reaction. So considering the machine in the linear representation, so linearly, if you expand that both ends, whatever I said previously, the armature looks straight line and poles also like this. What is the gap under the pole from one end to other end? Same constant gap, na? In the actual machine diagram also, same like that only. See, gap from this end to this end, same gap, uniform, same as it is we get here also. Same constant gap from one end of the pole to other end of the pole. Okay. Now there are some conductors. So here we have to draw three signals again. First main flux, second armature flux, and third resultant flux. First main flux. Main flux we have to indicate. So under north pole, what is the flux direction always? Comes outside the pole or goes inside the pole? Comes outside. When there is main flux, the flux is distributing uniformly from one end of the pole to other end of the pole, uniformly distributed. And towards the brush axis, what happens to air gap? See, what is the gap here? Increasing. So more gap at the brush axis. Similarly, at the south pole, flux will go inside uniformly throughout that. Flux distribution is same, constant throughout the pole. And what is the gap from here up to brush axis? Gap increase. So more gap is along brush axis. This is our GNA or brush axis we call. Now, what is the magnitude of flux from this end of the pole to this end of the pole? Almost constant gap. Flux magnitude is constant. From one end of the pole to other end of the pole, the flux is constant. Let it is positive. I'm taking under north pole, the flux I'm taking as positive. Now under south pole, what is the flux? Negative, opposite to north pole, no? Negative. Let us take it is negative. Constant. Why constant? Same gap. Magnitude of flux is constant throughout that. Now from this end of the pole to brush axis, what is the flux? Along the brush axis, gap is high. The flux is almost zero there. Flux is zero. Along the brush axis, there is no effect of north pole, no effect of south pole. That is zero, neutral, that is no flux. Similarly, here flux increases and again flux decreases, flux decreases. So what is the shape of that main flux? Already we know this, flat top. The shape of main flux is flat top or trapezoidal shape or trapezoidal. Okay. This is first one, shape of main flux is trapezoidal shape. Complete this first. Quadrature means 90 degrees. Armature flux will come exactly perpendicular to main flux. That is we call quadrature. Completed. Next, second, armature flux. So I'm drawing in the same page. Okay. So all of you draw now itself. So in PDF also it won't be available because I will remove here this and I will draw armature flux in same diagram. Armature flux, second one. Armature flux. See here. So मैं कभी भी कॉपी पेस्ट नहीं किया पहली बार. Okay. So यहाँ तो easy, मगर ऑफलाइन में कॉपी पेस्ट कुछ भी नहीं कर सकते जनरल. Next, only armature flux. See, for only armature flux, you have to remove this main flux. See, armature flux. फिर से क्यों क्रॉस मैग्नेटाइजिंग ऑलरेडी हो गया ना वो. So, ऐसे फिर बैक गए तो फिर so much time it will take. Okay, जब टाइम में देखेंगे हम, पहले इसे कंप्लीट करें. So observe here, armature flux we have to draw, but armature flux directly we cannot draw. That's why first we draw armature MMF. What is armature flux, or what is the flux generally? MMF by reluctance. Okay, that's why first we draw MMF. First we will draw MMF, and reluctance is depends on air gap. Now by considering that air gap variation, we will draw armature. By considering that reluctance variation, we draw armature flux. Okay, first armature MMF I am drawing, but that armature MMF I am drawing directly. Right now, directly I am drawing. In after completion of this, I will take separately how that armature MMF we are getting. Okay, this is armature current. Armature MMF will be like this. This is armature MMF. This is the armature MMF. So how we get this armature MMF? I will take another figure. There I will show you. So right now, draw this directly. This is armature MMF. The shape of this armature MMF is triangular shape. That is important. Triangular shape. So how it is triangular, I will show you again. Okay. Now there is armature MMF. Once you know armature flux, you can draw now. Flux proportional to MMF. Flux inversely proportional to reluctance. That reluctance is depends on air gap. Okay. Now observe, from this end of the pole to this end of the pole, what is the gap here? Constant. If air gap is constant, what is the reluctance? Constant. Now flux proportional to MMF only. Whenever air gap is constant, reluctance is constant. Then flux proportional to MMF. However, MMF is varying, in the same way armature flux also vary. Okay, now observe armature flux. From this end of the pole to this end of the pole, the flux is almost same as it is MMF. Okay, this is the variation of armature flux. Why it is varying like this? Because from this end of the pole to this end of the pole, what is the gap here? Constant. So reluctance constant. Now armature flux proportional to MMF only. That's why MMF is this, but armature flux little less than MMF. The reason is due to some small reluctance here, some gap. That's why it is I taken little less than that. Linearly varies. Similarly, under South Pole, from this point to this point, it varies linearly. So from this point to this point, linearly varies. Okay, proportional to MMF. If MMF is straight line, armature flux also straight line. It is proportional. But observe, from this end of the pole to brush axis, what is the gap now? Increase, 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 increase. So whenever gap increase, reluctance increase, your armature flux decrease. So flux decreases. This is the brush axis. Again, from this end to this end, if you consider gap increase, increase like that, increasing up to brush axis, then what is the flux here also decreases. So you will get a variation like this. Similarly here, again brush axis will come here. Again flux decrease, again flux decrease. So this is the shape of armature flux. This black one is armature flux. What is the shape of that armature flux we call? What is the shape of this armature flux? That is called saddle shape, not sadist, saddle shape. The shape of the armature flux is called saddle shape. See, I already said how that MMF we are getting. I will show you in separate diagram. Okay. Armature flux we are drawing based on MMF and reluctance. From under the poles, what is the gap from this end to this end? Constant. That's why linearly I drawn, because flux proportional to MMF only, linear. But from this end of the pole to brush axis, this is brush axis, no, GNA is nothing but brush axis. Same. So here gap increase, increase, increase. That's why flux decrease. But it won't zero here. A small amount of flux is there, armature flux. This shape we call saddle shape. What is the saddle shape means? So have you seen the horseshoe shape? Horseshoe. Horseshoe shape is nothing but saddle shape, like U shape it is, like this. This is the shape of horseshoe. Have you seen all of it? Horse itself we have not seen properly. Then where we can see horseshoe? Okay, if you want, refer in the Google. Horseshoe shape is like this, U shape. In the same way, this is we call saddle shape. In the same way, this armature flux also looks. That's why we named it is saddle shape. Saddle shape. Okay. How main flux means? Under the pole, what is the magnitude of flux? Constant. So constantly drawn. Under south pole, same gap, constant flux, but negative, because north pole we assume positive, it is negative taken. And from this end of the pole to brush axis, gap increase. That's why flux decrease. Whenever air gap increase, what is the reluctance? Increases. Then what is the flux? MMF by reluctance, flux decreases. That's why it is decreased. Okay, clear now? Next, all of you draw on the second. Now third one, resultant flux. Third one, resultant flux. So resultant is nothing but in your book only observed, because in your book at a same page you have both main flux and armature flux. Now at each and every dotted line here, each and every axis, add main flux and armature flux. Add both add main flux and armature flux, you will get one resultant flux. So the resultant flux how we get is, see here. Third one, resultant flux. See, third one, resultant flux, how we get it is. See, when there is both armature current, that is armature flux, and main flux, how the resultant flux we get? Under North Pole cross, under South Pole dots. Now, under North Pole, due to armature reaction, most of the flux is at where most of the flux is concentrating, resultant flux at one side, at one pole tip. So armature is moving in this direction. Assume that armature, this is armature only, moving in this direction. Then it is the trailing leading pole tip, it is the trailing pole tip. So under North Pole, flux distribution, very small amount of flux here, and towards the other pole tip, flux density increases. So here we have more flux density at this pole tip, and under the south, very less amount of flux here. Very less amount of flux, and towards this pole tip, flux density increase. So this is flux distribution under the pole, same as previous diagrams, representing in this diagram also. Okay, most of the flux lines is at this pole tip. Now if you draw accordingly, at this pole tip here, the flux is very small, a small amount of flux at this pole tip. Now towards this pole tip, flux density increase. So most of the flux is at this pole tip. Most of the flux is at this pole tip. Now along the brush axis, observe the main flux 0. Observe at the brush axis. Observe at brush axis. Main flux is what? 0. But what is armature flux? Not 0. Previous figure. Armature flux is not 0 here. But what is main flux here? 0. At the brush axis, main flux is 0. Armature flux is not 0. Then if you add these two, what is the resultant flux? Not 0. The resultant flux is not 0 at brush axis. So somewhere here it is 0. Okay, not 0 it is. This is due to armature flux here. Now you will get 0. After that, somewhere you will get 0 here. Now again under the south pole, flux density variation is like this. Okay, most of the flux is concentrating at this pole tip. Okay, this is the peak at the pole tip it is. Why this is? Most of the flux is at trailing pole tip. So this is the trailing pole tip here. This is the trailing pole tip. Okay, this is the resultant flux shape. What is the shape of that resultant flux? Is peaky wave. Remember, the shape of resultant flux is peaky wave. It is the sum of main flux and armature flux. In your book, in your page, you add both and you will get this relation only. This waveform only you will get. Add main flux and armature flux. Okay. Now in this figure, where is the MNA? Tell me. Where is MNA in this diagram? Magnetic neutral means no effect of north, no effect of south. Where is that? This point. So this is the neutral axis. See, this axis is the neutral axis. Wherever flux is 0, that axis we call neutral axis. That is MNA it is. This is the MNA. MNA shifted from GNA in the direction of generator. Okay, it is MNA here. Magnetic neutral axis is this. But observe, where is the brush position? Brush is at GNA. If brush is here, along the brush axis, there is some flux or not? Yes. You observe the first figure, main flux. Observe the main flux. This is the brush axis. And here the flux is 0. This is the brush axis. Along that brush axis, flux is 0 here. That's why when there is only main flux, means no load condition. No load condition, only current 0 in this. Observe, armature current 0, no load. Then only main flux is there. When there is only main flux, what is the flux along the brush axis? 0. That's why there is no spark at brush. At that time, you don't get any spark. But when there is armature current, it causes a reaction. Due to that, where is the MNA now? Here. This is the flux 0 point. But along the brush axis, some small amount of flux is there. This small amount of flux will cause an EMF in the coil still. Due to that EMF in the coil, a current will circulate. Due to that current only, we are getting spark at brushes. Now tell me, if you want to reduce the spark, along the brush axis, what should be the flux? 0. Along the brush axis, the flux should be 0. Then no EMF, no current, no spark. But due to armature reaction, this is not becoming 0. Now, what is the main effect for this? Cross magnetizing effect. Due to that only, waveform is distorted. That's why some flux we are getting at brush axis. If it is not distorted, the flux will become 0 here. Along the brush axis, flux will be 0. Okay. Now tell me here itself. If you want to reduce spark at brush, you need to shift the brush or not? Yes. If you want to reduce the spark, you need to shift the brush onto this MNA. Wherever there is MNA, shift the brush there. Because what is the flux here? 0. Now you don't get any spark. Okay. If you shift the brush onto MNA, magnetic neutral axis, there is flux 0, no EMF, no current. You don't get any spark at the brush position. This is one method to reduce the spark. But in ESC interview in one of the year previously, one student faced this question. They asked first, what are the reasons for spark at brush? And he given some reason, that armature reaction reason, he said mainly. Then they asked, how can you reduce spark at brush? Then he said, by shifting the brush onto MNA, we can reduce the brush. Now their question is, how do you know where is MNA first? Not in this figure. Tell me in this figure. Suppose it is our armature. Okay. Actually, brushes are along GNA. Consider this is the brushes. Brush axis or GNA, it is geometrical neutral axis. Now, due to armature reaction, MNA shifted. In which direction MNA shifted? In the direction of generator. So I'm not drawing complete figure, just observe here. This is the MNA. Okay, this is our MNA, magnetic neutral axis, shifted from GNA. Shifted from GNA by some angle theta. Now you said that if you shift the brush in the direction of generator, that is onto MNA, the spark will reduce. This is clear. Spark will reduce definitely. But their question is now, how do you know where is MNA? So first of all, can we shift the brush practically? Is it possible? Where is the brushes? Inside the machine. How can you shift? Can you shift easily? If you touch the brush, it will throw you outside. Then how can you shift the brush? Okay, practically not possible to shift. Practically not possible to shift. But still, let us consider brush is shifting. How do you know where is MNA? If you know that MNA is here, you can shift the brush. Then what is your answer? Tell me, interesting it is. How do you know where is MNA? How do you know where is MNA first? So that you can shift the brush onto that point. How do you know that? That angle only. How much angle MNA shifted? That we should know, no? Otherwise, how can we shift? How do you know that angle? You can say easily this answer. Okay. Resultant MMF. Okay, all this. Yes, Masood, you said right. Magnetic compass. So that much things are not available. Simple. Suppose brushes are here. Brushes are here now. Now you are getting heavy spark at brush. To reduce the spark, you need to shift the brush onto MN. So how do you shift? Suppose I don't know where it is MN. So what you can do is, let us move the brush slowly. Move the brush slowly, step by step, step by step, step by step, step by step. At one position of brush, you don't get any spark at brush. That is only the MN. Simple reason. Shift the brush. You don't know where it is, but let us shift slowly, step by step, some angles. Shift the brush, shift the brush. At one position of the brush, you don't get any spark. That is only the MN, magnetic neutral axis. There, fix the brush. But practically, how we fix the brushes in the machines is, because practically no one can shift the brush. Whenever it is operating under running condition, you cannot shift the brush. How during manufacturing we fix the brushes? Observe here. Suppose this is actual GNA position. This is no load position. This is the no load. Then no spark at brush. When there is load connected to generator, some MNA will shift by some angle theta. Assume that theta is totally 10 degrees. MNA shifted by 10 degrees at the full load condition. But is it always like every generator or every transformer, we always operate at full load? No. A generator, you may operate at full load or half full load or 70% or 80%, anywhere we can operate. That's why if it is full load 10 degrees, half full load approximately 5 degrees. Now they will fix the brush at the midpoint. On an average, at one place, they will fix the brush. You may operate at no load, you may operate at half full load, you may operate at full load. Anywhere if you operate, the spark is less. Spark is less. Like that, they will fix the brush and you cannot move the brush further. Practically, we cannot move the brushes. Fixed one it is. Okay. Now let's see how the armature MMF is triangular. Let's start heading armature MMF. Armature MMF. How it is triangular, observe here. For that, I will consider an armature. I will consider an armature with 6 slots. Brush axis. So I'm considering an armature with 6 slots like this. The slots are there. And how many coils I can place here? Single layer winding, suppose. How many coils I can place? That it is 0 degree, 30 degrees, 90 degrees, 150 degrees, 180, 210, 270, 330, 360 again. There are 6 slots. Single layer winding. How many coils we can place? Half of that means 3 coils. Now one coil side, one coil has 2 sides. One side I will place here, another side I will place here. That is 1, 1 dash. Okay. Next 2, 2 dash. This is one coil. Like that 3, 3 dash. This is one coil. 3 coils I placed. Now assume that left hand side is under north pole, right hand side is under south pole. I'm not drawing poles. You try to imagine. This is north pole is there, south pole is there. Whenever it is rotating clockwise, what is the current direction under north pole? Cross, cross, cross. Under south pole, dots, dots, dots. So under north pole, current is cross, and under south pole, current is dot. Cross and dot here. If you rotate clockwise, so the direction of current we are marking by Fleming's right hand rule. Okay. Always it is cross only under north pole. Why it is always cross? Because motion of conductor under north pole is upward direction. Upward direction. That's why always cross only will get. Under south pole always dot only will get. Okay. Now observe. Now I will consider this armature linearly. Let us cut here. Cut here. Assume that paper it is. Cut here and expand the both ends. Then your figure looks like this. Your figure looks like this. So same armature I'm drawing linearly. So representing linearly like this. Observe. So let it is 0 degree here. This is 30 degrees, 90 degrees, 150. This is 180 brush axis, 210, 270, 330, 360 it is. Okay. So same armature I taken linearly. Linear representation of this. Now coil 1 present 30 degrees it is. 90 degrees, 150, 180, 210, 270, 330, 360 degrees. Okay. Now under north pole, what is the direction of current cross? This is 1, 1 dash, 2, 2 dash, 3, 3 dash, 2 here. Under south pole current is dot. So in order to find the MMF shape of MMF, what is MMF? Number of turns and current. Okay, ampere turns. But what is the turns in every coil? There are 3 coils here. 1, 2, 3. 3 coils. Every coil will have same turns or not? Yes. In every machine, each and every phase or each and every coil will have same number of turns. Like that we place for balance in each and every phase. So number of turns is anyhow fixed. That's why I will remove that number of turns. Now MMF proportional to variation of current. Now observe each and every coil. Coil 1, coil 2, coil 3. In each and every coil, after for every 180 degrees, there is a change in current in the coil or not. See, here in coil 1 cross. After how much angle the current in the same coil will reverse? After 180 degrees. That is dot here. If it is cross here, here it is dot. So that change in current will decide the MMF. So for every machine, not only DC, for synchronous machine also same as it is. Armature MMF. So observe here. First I will draw the variation of current in each and every coil. For each and every coil I will draw first. Then I will take the resultant of 3 coils. See at coil 1, here it is cross. Cross I will take as positive. Cross means I am taking positive. Dot means negative. Dot means negative. So cross is positive. So here positive. After how much angle current in the same coil changes? Negative here. So minus. -1. Let +1 and it is -1. Any value you can take, +1 or +10 or +20, +100, anything. Just example, I am taking +1, -1. Positive, negative indication it is. This is for coil 1, 1 dash. Similarly, coil 2, 2 dash. Where is coil 2? 90 degrees here. What is the current here? Cross, positive. After how much angle current changes in this? At 270. After 180 degrees. This is negative, -1, +1. This is -1. Variation of current I am considering in each and every coil. Based on that only MMF we get. Similarly, 3, 3 dash. 3, 3 dash. Where is 3? 150 degrees. Positive here. After 180 degrees at 330, negative it is. -1, +1, -1. Okay. Now I drawn individual coil currents. But MMF, armature MMF is total resultant we have to take for all coils. Now the resultant, let us draw here, resultant of this 3 coils. Resultant current. Observe at 0 degree, this is -1, this is 0 degree. So this is -1 and this is also -1, this is also -1. What is total? -3. Total is -3. Let at 30 degrees, this is changing, transition is there, that is -1 to +1, average 0 we take. So it is -1, it is also -1, -1, -1, -2. Okay. Similarly at 90, this is +1, 0, -1, +1, -1, 0. Next at 150 degrees, +1, +1, +2, this is 0, so +2. Okay. Next at brush axis, exactly +1, +1, +1, this is +3. So if you join all these points, you will get a straight line. Similarly, you draw here also. Similarly here, +1, +1, +2, -1, 0, +1, 0. Again, -1, -1, -2. Here at 360 degrees, -1, -1, -1, -3. Okay. If you join all these points, you will get a triangular shape. Triangular shape. But actually, it won't come directly triangular. Here for 3 coils, it won't be triangular. I will give why it is not triangular. First, it is a triangular. Important here is, this is in engineering services also, previously in prelims, one of the examination they asked. The shape of armature MMF is dash triangular. This is the peak of the triangular. This is peak. The peak of the triangular is along which axis? Brush axis or interpolar axis. What is the other name of this brush axis? We call interpolar axis. And where is the polar axis here? 90 degrees. This is the polar axis. Polar axis is this. See, if you place the poles, it is the center of the polar poles. Polar axis it is. Okay. There is a pole here. You will get like this. Now, what is the polar axis? Passing through 90 degrees only. This is only polar axis. Okay. Now, important is the shape of armature MMF is triangular with the shape of armature MMF is triangular with its peak is along with its peak or maximum value is along interpolar axis. Interpolar axis. And the armature MMF is 0 along which axis? This one, polar axis. 0 along polar axis, maximum along interpolar axis. See, actually you don't get triangular directly. Stepped wave you get. Stepped wave. But when it is triangular, so first complete, I will draw that. First complete up to this. Yes, very good. For more number of coils, you will get triangular. But for less number of coils, you don't get that. You will get steps only. A stepped wave you get. So MNA axis is fixed one. It won't change again. Observe. Completed all of this. Observe this. Actually, you don't get triangular wave. You will get a stepped wave here. See this. Actually, from 0 to 30 degrees. Let us take each and every duration separately. From 0 to 30 degrees, what is this -1? What is this -1? What is this -3? This is -3. From 30 to 90, +1, -1, 0, minus. This is +1, -1, 0, -1. So, right. -3 here. 0 to 90 degrees, -1. Is it same? Oh, same, right. So like this you get -1, -1, -1, -3, and 30 to 90 degrees. This is +1, this is -1. +1, -1, 0, and it is -1. So you get -1. Next, from 2 to 3, +1, +1, +2, and this is -1. That is +1 you will get. Next, from 3 to, that is 150 to 180, +3, +1, +1, +1, +3. So okay, like this you will get. Like this you will get. Like this you will get a stepped wave you get. You don't get triangular directly, but when you will get triangular, assume that there are 20 coils. If there are 20 coils, you will get the steps very near, very near, like this. 20 coils, if it is there, you will get like this. Then if you join all the points approximately, you will get like a triangular shape. Okay, clear now? Triangular will come only for more number of coils, but directly I am showing with a less number of coils itself, it is like a triangular wave. Clear now? Because you should not get after some time again how it is triangular directly. It is not triangular for less number of coils. Stepped wave like this only will get. Okay. So clear all of this. Right now, effect of brush shifting. So what happens if you shift the brush? Effect of brush shifting. So in which direction we have to shift the brush actually? Generator direction or motor direction? In which direction we have to shift the brush? Generator direction. Because if you shift in the direction of MNA, wherever flux is 0, then you don't get any spark. But there are some questions regularly we are getting in the engineering services and many places competitive examinations also, like if brush is shifted in the direction of generator, what happens? And if brush is shifted in the direction of motor, what happens? So this is important questions. Now we will see both cases simultaneously. Right, first case one. If the brushes are shifted, if the brushes are shifted in the direction of generator. Let's see what happens. In the direction of generator, then what happens if the brushes are shifted in the direction of generator? Now first I will take what is normal brush position first, then we will shift. See, initially this is our main flux, this is our armature flux, and due to the reaction of these two we got one resultant flux. Okay, and GNA is fixed always. This is GNA, geometrical neutral axis. And where is the brush axis? Actually along GNA. This is the brush position. But due to the reaction of effect of armature flux on main flux, we got one resultant flux. This is our resultant flux. Now where is the MNA? Perpendicular to this resultant flux. This is our MNA. Okay, perpendicular to that resultant flux. Consider the machine representation also. Consider this. This is actually brush position. See, important it is. So here we have number of conductors. Okay, this is GNA, geometrical neutral axis. What is the current actually with respect to brush position? Remember, currents will reverse at brush positions only. Current in armatures will reverse at brush positions. Okay, now when it is a brush position, here there is cross. When it is brush position, one side is cross, other side is dot with respect to brush axis. Okay, now what is the armature flux? If you apply right hand thumb rule, the armature flux I am getting downward direction. This is the armature flux by right hand thumb rule. Okay, cross dot, flux is downward direction. So this is when brushes are here, armature flux is this direction. Now we need to shift the brush. Which direction? This is generator direction, this is motor direction from previous figures. Where is the MNA now? Here. This is MNA. Let us consider this is our MNA. This is MNA, magnetic neutral axis, shifted from GNA by some angle theta. Let us consider it is shifted by an angle theta. Now same angle theta, you have to shift the brush. Let us shift the brush onto this MNA. Whenever brushes are shifted, what is the current with respect to brush axis? Should change or not? Always with respect to brush axis, current one side is be cross, other side will be dot. The same will applicable here. Now see, to the brush axis, this is cross, it will become dot. With respect to brush only, current will reverse always. At brushes only, current reversal takes place. Okay, now brushes are shifted. Brushes are shifted by same angle theta. Now if you shift the brush in this figure, in this in the direction of generator, this is the new brush axis. If it is the brush axis, observe now, apply right hand thumb rule again in the figure. Apply in this figure right hand thumb rule. Cross dot, armature flux is coming in this direction or not? Yes, armature flux is coming now in this direction. This is armature flux. Cross dot, cross dot, armature flux is downward, little angle. Now armature flux will come along the same brush axis. This is armature flux. After shifting brush, this is the armature flux. Okay, now what happens? This armature flux is resolved into two components. One is along this axis, one is along this axis, and another is along this axis. Armature flux is resolved into two components. One is along main field axis, one is along quadrature axis. So this is we call phi AC. This is we call phi A D. D means, what is D? Demagnetize. C means cross magnetize. Whenever the brushes are shifted in the direction of generator onto MNA, what is the main purpose of shifting brush? To reduce the spark. So spark will reduce or not? Along the MNA, no brush is placed. As brushes is now along MNA, what is the spark at brush? No spark. There is no spark at brush. Spark is reduced. But there is a drawback here. What is the drawback? Due to that, now there are two effects: demagnetizing effect, cross magnetizing effect. Already demagnetizing is there due to saturation. Due to saturation of coal tips, there is a demagnetization. Now there is additional demagnetizing effect because this flux is exactly opposite to main flux. Just like in alternator, exactly demagnetization, purely inductive load. Flux will come, armature flux will come exactly opposite to main flux. That effect we call demagnetizing effect. So additional demagnetizing effect we are getting if you shift the brush in the direction of generator. But what is advantage? Spark is zero, no spark, but which is important to you. So because of demagnetization, what happens? Overall flux reduces, EMF in generator still reduces. EMF still reduce. This is drawback. But what is want for us? What is want? What is important? Voltage important or motor safety important? Suppose if you don't shift, spark is continuously coming. Then your motor or generator will die totally. Then no use of generator and motor. That's why if you shift the brush, advantage is spark is reduces. But drawback is due to additional demagnetizing effect, some more flux in generator will reduce, which reduce the voltage of the generator still little bit. Voltage reduce, no problem. Some small voltage reduce. But important is safety of motors and generators. Okay. So finally, if the brushes are shifted in the direction of generator, what happens? Spark will reduce. But due to additional demagnetizing effect, the flux in generator still reduces, which reduces EMF of generator. This is drawback. And there is one more point here. It will improve commutation. Commutation is not completed after armature reaction. We see commutation. So remember here, improve commutation. Improve commutation means spark is reduced. That's it. Improve commutation means spark reduces. And there is one more term, deprove commutation. Deprove means decrease. Decreasing commutation means spark increases. Because remember here itself, in commutation, this we have to discuss again. Okay. So write one statement. First take the figure. Take the figure. Right here. If the brushes are shifted in the direction of generator, if the brushes are shifted in the direction of generator, then spark at brushes reduces. Spark at brushes reduces, comma, which improves commutation. Which improves commutation. Which improves commutation. But an additional demagnetizing effect takes place. An additional demagnetizing effect. An additional demagnetizing effect takes place, which reduce the flux in generator, flux in machine further, which reduce the flux in machine further. It is drawback, but main advantage is spark reduces. That is we want. EMF reducing is no problem. You can increase the EMF by increasing number of turns if you want. Okay, but main problem, whatever is there, spark is reduces. That is important for us. So these are the conclusions for whenever brushes are shifted, improves commutation, but due to additional demagnetizing effect, flux in machine reduce. Because of that, EMF reduces. See, if it is motor, EMF reduce. If it is generator, EMF reduce. If it is motor, which one will reduce? Torque will reduce. At the same time, if it is motor, torque will reduce. Okay, remember these statements. Direction of generator means clockwise, no? Clockwise. Generator, we are rotating clockwise. Spark will reduce almost. How spark will reduce? So in this figure, you cannot identify. Observe this figure. If you shift the brush in the direction of generator, that is wherever MNA is there, if you shift their brushes, what is the flux at that time? Zero. If flux is zero, no EMF will be there in the coil, no current, no spark. So in commutation, you will get clarity again, how spark is reduced. In that commutation topic, you people will get clarity still, how spark is reduces. Okay. Next, it is one first case it is. If the brushes are shifted in the direction of generator. Now, right, last one. If the brushes are shifted in motor direction, what happened? Completed all of this. Right now, second case. If the brushes are shifted in the direction of motor, if suppose by mistake wrongly you shifted, then what happened? We have to know that. Right, that if the brushes are shifted in the direction of motor, in the direction of motor, now check what happens. So again, consider without shifting brush, first figure. Without shifting, this is the main flux, this is armature flux, and this is GNA. Along this axis only we have brushes. This is GNA. Along this axis, brushes are there now, right now. Now, resultant flux we got due to effect of armature flux on main flux. This is resultant flux. Now, MNA shifted perpendicular to this. This is MNA. Okay, magnetic neutral axis shifted. Now, let us shift the brushes opposite to MNA. MNA shifted in generator direction. Now, let us shift the brush in the direction of motor. This is motor direction, no? Opposite to generator. This is generator direction. Motor means anti-clockwise direction. Now let us shift the brush by the same angle, whatever is there theta, same angle you shift in this direction. Same angle brushes are shifted. In opposite direction shifted by mistake. Now, if it is the brush position, where is the armature flux, tell me? Along the brush axis or not? Armature flux is always along brush axis only. Okay, just like previous one, I'm not drawing. If it is the brush axis, armature flux is along that. If brush axis is here, if brushes are here, now armature flux also along the same axis. Okay, the armature flux is along the same axis. This is armature flux. Now, if it is the armature flux, now again it is having two components or not? Yes. One is along main flux. This is we call phi AM. One is along cross magnetizing. This is phi A C. If the brushes are shifted in motor direction, there is an additional magnetizing effect. So when magnetizing effect will come in machine, if in the generator, if brushes are shifted in motor direction or opposite to generator direction, generator clockwise, by mistake brushes are shifted anti-clockwise, that is motor direction we call. Then what happens here? There is additional magnetizing effect. Now what is the resultant flux? The resultant flux increases. If flux increase, What is EMF in generator? Increase. What is torque in motor? Increase. This is advantage. But what is the main problem? Tell me. What is the main problem? By mistake, you shifted in motor direction. What is the main problem? The spark you will get at the brush position is so much dangerous spark. The spark you will get dangerous. Definitely it will damage the entire DC machine. Is it important? Do you want magnetizing effect? Never. Magnetizing we don't want because dangerous thing if you shift the brush. Why? Because observe the figure. See, it is generator direction. It is motor direction. If you shift the same brush towards this, flux increase. Suppose if it is the brush axis, flux is very high. Due to that high flux magnitude, high voltage, high current will flow in the winding, and that current will appear as a spark at brush. That's why we should never shift the brush in the direction of motor. So where we have to shift the brush? In the direction of generator. So take the figure first. That is called bad commutation, right? Or commutation deprove. Right statement here. Therefore, if brushes shifted, if the brushes are shifted in the motor direction, see these conclusions you should remember. This is only the objective questions. If the brushes are shifted in motor direction, see sometimes they call motor direction, sometimes they call opposite to generator direction to confuse. Opposite to generator means motor only. Okay, if the brushes are shifted in motor direction, then there is an additional magnetizing effect. Additional magnetizing effect, which increase the flux in machine, which increases the flux in the machine, which increases the flux in the machine. So if flux increases, EMF increase in generator, torque increases in motor. This is generator, this is motor. EG increase, torque increase. But what is the main problem? But the magnitude of spark increases. Magnitude of spark increase rather than decrease. Magnitude of spark increases, which damage the entire machine. Which damage the entire machine. Okay. So never shift the brush in motor direction. So here they will give in commutation. What happens to commutation now? Commutation will deprove. Previously commutation increase. Commutation increase means spark reduce. Now spark increases means commutation deprove. Commutation deprove or simply bad commutation. Bad commutation we get. Okay. So still armature reaction not completed. Now in the next class we have to find this one. Whenever brushes are shifted, there we have demagnetizing effect. So demagnetizing is due to how many conductors. So there are so many conductors in armature. In that, how many conductors causing mainly demagnetizing effect, and how many conductors causing mainly cross magnetizing effect. That is called demagnetizing ampere turn per pole and cross magnetizing ampere turn per pole. If you get any numerical from armature reaction, only this calculation you get. So that we will see tomorrow. So after completion of that, again methods to reduce the effects of armature reaction. So with that, armature reaction will complete. Then we start commutation. Okay. So tomorrow we continue the same timing. See, practically we cannot shift. That's why I already said that point. Practically we cannot shift the brush. If it is required to shift, this is the conditions. Okay. Yes.
Sir,
Tell me.
in this page only, sir, here how we get demagnetizing and cross magnetizing, sir. Can you please explain that once again?
See, when armature flux is this one, previous one. When it is armature flux, if brushes are along GN.
Armature.
At that time, there is only there is only cross magnetizing effect. No, armature
Yes,
flux
sir.
perpendicular.
Okay, sir.
But when brushes are shifted on MNA, this is the armature flux.
Okay,
Now,
sir.
now it is making some angle. No, with respect to that, we will divide into two components.
Oh, okay, okay.
Just like alternator, you drawn phasor diagram, same as it is.
Okay,
Cross
okay, sir.
magnetize, demagnetize, both will come.
Okay, okay, sir. Thank you, sir. That's it, sir. Thank you.
Hello, sir.
Tell me.
Hello.
Prashant.
Hello, sir.
Tell Prashant.
Sir, I had a doubt when windings will weaken. Yesterday, sir.
When?
Windings will weaken its strength. Then how to improve that? Hello.
Tell me.
Sir, in series generator, sometimes we kept thin wires, na sir.
Yes. Series thick wire.
Sorry, sir. Shunt.
Shunt field thin wire.
Thin wire, na sir. When it damages, what will happen? That means it
open circuited.
Yes, sir.
That we will see in the coming classes.
Okay.
Okay.
Hello, sir.
Tell.
Sir, this brush shifting is not practical, no, sir. Sir, what is the method we are using for the reducing spark? Is it in next class?
Interpoles, yes. Methods to improve. Methods to reduce armature reaction. There you will get. Interpoles we use, compensating winding we use.
By this sparking will reduce.
Yes.
Okay, sir.
So good evening, sir.
Tell Shiva.
Sir, at 48 Fs. Sir, here could you explain me the distortion of flux lines one more time?
Which one?
Distortion of flux lines. That is towards the.
It is due to armature flux, no, simply. See, simply our main flux is actually I shown already in this diagram. Here, actual main flux is coming like this. But how armature flux is coming like this?
Okay, sir.
Now, main flux will deviate like this or not? Because of effect of armature flux, it won't come straightly because armature flux line is coming in this way. This armature flux line will deviate main flux towards upward direction. That's why resultant we get like that.
But under south pole, why it is like towards the.
There also this one. How armature flux here downward direction.
Yes, sir. Okay.
Now how armature flux here in this direction. So however armature flux is flowing in the same direction, it will deviate.
Oh, okay, okay, sir. Okay, got it.
Okay.
So those two fluxes won't cut each other, like.
Yes.
Okay.
They are distorted. It is distorting the main flux.
Okay, sir. So due to this, the accumulation of flux lines will be at the trailing voltage. So that effect is called as strengthening.
Yes.
Okay, sir. That's it, sir. Thank you, sir.
Hello, sir.
Tell.
Hello, sir.
Bimal in this one.
Sir, the graphical representation in armature reaction here that MNA is shifted. So yes, that position is the for the brush we are getting 0 that is in, for that brush position we are getting 0 sparking.
Yes.
Okay. But when you are drawing that diagram, the last diagram, that
Mm.
the motor direction is shifted, but that phi A will be same because it does not depend on the brush position. Because that phi A will be in the same as generator direction. But your means I have doubt that phi A will be changing. Means when we are changing the
Yes.
brush position to in the
Uh.
direction of motor,
Yes, yes.
phi A you are
Phi A will change. Maybe I think your doubt is like if it is shifted in motor direction, accordingly phi A will change. Then what happens here?
because that phi A is a signature, so it is does not depend on the brush position. Brush is the outside, but inside only that phi A will be why that phi A will be changed.
But anyhow,
Because
there is effect of armature flux on main flux. No, we should not consider only armature flux. Main flux also we should consider. Both react. That resultant we have to consider. How
yes,
can we
but
take
that
only armature flux?
but sir, that you are showing that cross current shifted to MNA axis, that will be the same. That is shifted will be same, but brush shift
This one?
we
This one?
depend on us. Yes, sir. That last one. That yes, sir. That phi A we are showing in case of that same machine only we are changing the brush position. But not changing that phi A. Phi is the internal behavior of that machine. This will be depend on how it is rotating.
No, it's actually new phi A is this one. No? So at that time it
But
won't
why,
be there.
sir? But why, sir? That phi is depend on brush.
So only at brush positions, current will reverse in the windings. So if you see the armature winding diagram, current reversal taking place at which position? At brush position only.
Yes, sir.
And one more is in commutation. Next topic in the next topic you will understand. Current reversal every time takes place at brush position. So that I will show you in the commutator. Okay.
And phi definitely will be changed.
Oh, definitely changes.
Okay. Thank you, sir. Another doubt is that we are taking minus 1 plus 1. Here that 180-degree electrical. Inside that it is AC nature, the current is AC nature, but we are taking it like a square wave.
But approximately it is when there is less number of coils, approximately it is square nature. But actually, how many coils will be there in armature?
More number of
three coils. No, there is maybe 18 coils, 24 coils, like that will be there. Then almost triangular only will get resultant.
Sir, I am asking about that only 1 dash 2 dash individually. It will,
yes, individually that is nothing but variation of current in the coil. No? Under north pole cross, under south pole dot. For each and every coil, it is changing under north and south. No? When it is rotating.
Why not it will sinusoidal? Sir?
Why not sinusoidal means what is the variation of flux we are considering? Flat top.
Okay.
That's right.
Okay. Thank you, sir.
Hello, sir.
Mahesh.
Sir, how is MNA is perpendicular to resultant flux? Sir? How is MNA is always perpendicular to resultant flux?
See, there are two definitions. One definition is that, and another definition is what? According to these figures, resultant flux, wherever it is 0. So wherever there is no effect of north pole and south pole, that axis we call MNA. But in the machine representation, means machine diagrams like this. In these machine diagrams, it is defined as resultant. MNA is always perpendicular to resultant flux because under no load condition, what is the resultant flux? Under no load, only main flux is resultant.
Yes, sir.
Then where is MNA? This is only MNA, perpendicular. But when there is load, reaction takes place. So we get some resultant flux. So at that time also, to the resultant flux only MNA perpendicular. Okay. Clear?
Yes, sir.
Hello, sir. Hello, sir.
Avinash, tell me.
Sir, will you explain the phi A nature of graph, sir?
Field?
Sir, 5A graph, sir.
Page. This one.
Yes, sir. This one, sir.
Oh.
Sir, it is proportional to the armature MMF, but at this point, it's a curved shape.
Where at point? Which point?
Sir, in the middle, black color.
Here.
Curve. Yes, sir.
At the middle.
Yes, sir. Yes, sir.
Oh.
Sir, how we have got that curve?
Because if you see also machine diagram. It is the rotor. This is pole. Observe here. See, from this end to this end, what is the gap? Almost same. Okay. From one pole tip to other pole tip, the gap is same, uniform. But from this pole tip to brush axis, what is the gap? Slowly increasing. Here gap is less. But towards the brush axis, what is the gap here? Increasing now. Okay.
Yes, sir. But sir, we are comparing about armature flux, sir.
Armature flux also. Armature flux pattern is this only, no?
Yes, sir.
Then it is depends on the reluctance variation or not.
Yes, sir. Reluctance.
That's why at the brush axis exactly, what is the gap with respect to pole tip to brush axis? More. So more reluctance means what is the magnitude of armature flux along that axis? Less. It will reduce. So accordingly, we have drawn at the brush axis exactly the flux is reduces and minimum at brush axis.
Okay, sir.
But not zero completely it is.
Okay, sir.
Okay.
So means at constant air gap, it will increase proportionally.
Proportionally to MMF.
And sir, in the last topic, sir, what is the significance of 5AC?
Cross magnetizing, no?
Yes, sir. 5AC component.
Cross that is now it is not perpendicular, it is not 180 degrees, but it is armature flux with some angle. That is, we resolve into two components. One is along cross magnetizing, that is perpendicular, and along the Q axis, along the D axis. Along D axis, this flux is exactly opposite direction. That's why we call demagnetized, and this is cross magnetized.
Sir, this cross magnetizing component will affect. It will affect or not, sir?
It will affect because cross magnetizing mainly causing distortion. Okay. But with respect to this magnitude of armature flux, what happens? Cross magnetize little decrease. Means distortion little decrease, but demagnetization is additionally coming. Just like in alternator phasor diagram, same as it is.
Okay.
With the different power factors there, 0.8, 0.6, 0.4 like that. Cross magnetizing will change, demagnetizing will change. Same as it is.
Sir, demagnetizing effect is more as compared to that, or
that depends on the shift, how much you shifted. But generally we shift very less, 10 degrees, 12 degrees like that we shift. So cross magnetization only more.
okay, sir.
Hello, sir.
Anil.
Sir, ఒక చిన్న ప్రాబ్లం డౌట్ ఉంది సార్ నాకు. ప్రాబ్లం రీడ్ చేస్తాను సార్. A 8-pole wave wound DC generator has armature resistance is equal to 4 ohms. If it is reconnected for lap winding, what is the armature resistance? In that I have a doubt, sir. General ante man lap winding kabatti connect.
Lap winding, each parallel path resistance R, then R by 2 equal to 4 ohms given, then R equal to 8 ohms. Each parallel path.
Yes, sir.
Now when we convert to lap connection, how many parallel paths will come in that? 8 parallel paths will come. Means the 2 parallel paths you have to convert into 8 parallel paths. How can you convert? Each parallel path let us divide into 4 equal parts. 2, 2, 2, 2. Now make it is 1 parallel path here. Like that, total 8 2s are there. 2 by 8, 1 by 4, 0.25 ohms. What is doubt here?
Sir, అదే సార్ ఇక్కడ కన్వర్షన్ నాకు అర్థం అవ్వలేదు సార్.
See,
how to split into
2 lines ni 4 lines 8 lines చేయాలి. ఎలా చేస్తాం?
8 లైన్స్ ఎందుకు సార్ మనకి?
8 parallel paths కదా మనకు కావాల్సింది. ఇప్పుడు 100 200 టర్న్స్ ఉన్నాయి మొత్తం.
ఓకే సార్.
200 టర్న్స్ అంటే ఈచ్ parallel path లో 100 టర్న్స్ ఉన్నాయి.
ఓకే సార్.
ఓకే. ఇప్పుడు ఇదే 200 టన్స్ ల్యాబ్లో కన్వర్ట్ చేయాలి. అప్పుడు 8 ప్యారలల్ పాస్ అంటే ఎన్ని టన్స్ పెట్టాలి ఒక్కొక్క దాంట్లో? 25 కదా పెట్టాలి.
ఓకే సార్. ఓకే సార్. ఐ అండర్స్టాండ్.
ఇప్పుడు అలా వస్తుంది అంతే కదా? అలానే కదా?
ఓకే సార్. థ్యాంక్ యూ సార్.
Sir,
Ah,
sir, that sadding shape, that waveform, sir, armature flux waveform.
ah.
Sir, here why that curve doesn't reaches to zero, sir?
Because armature flux totally not zero, no, along that axis. The poles is along the q axis only. That never be zero along that axis.
Oh, okay, sir.
Hello, sir.
Oh.
Sir, generally we place brushes to collect the voltage and give the current in case of generator.
Now your doubt is if it is zero, how we are getting current and voltage outside? That is only, no?
No, sir, that's one and this one also, sir. Then we say that at polar axis the EMF is maximum. Then we place the brushes at GNA axis, sir.
Polar axis?
We'll get the maximum.
See, one thing actually, electrical representation of brushes is along q axis. But physically, the brushes, if you see the machine directly, the brushes is along the polar axis only. Okay, placement of brush is along polar, but electrically we represent brushes is along q axis. That is different.
Sir, why, sir, will represent difference is there, sir?
That is because you observe the armature winding diagram.
Yes,
Complete winding. Lastly, I drawn one diagram. There, if you put the commutator segments and brushes, that brush positions you will get exactly under the center of the poles, approximate.
Okay, sir.
Because current reversal is taking place exactly at that position only. That's why brushes we have to place there. But electrically we represent here, because according to Fleming's right hand rule, where it is becoming zero here at the q axis. That's
Yes,
why we
sir.
place brushes here. That means that you don't say that if EMF is zero, what we are collecting. EMF we are not collecting at this point. If you see the armature winding complete diagram, there is current coming from so many coils at one place.
Yes, sir.
That is we have to consider.
Okay, sir.
Okay.
Sir, second one you have said just now, sir, that one also, sir.
One.
Sir, you have said starting this.
Oh, which one that is?
Sir?
Which one? I forgot.
Sir,
You also forgot?
yes, sir. Sir,
I remember tomorrow.
okay, sir. I'll ask him also.
Okay. Good night.
Sir.
Shubham.
Hello, sir.
Sir.
Shubham, tell me.
Sir, in both phi and the phi.
Huh?
Sir, that diagram.
Kamsa.
Sir, that both phi m and the phi.
IM and?
Phi m and phi at 48.
Page number?
48.
Oh.
Sir, here can you explain that from where the conductors are entering? And in motor side?
Motor side, huh?
Yes, sir.
Suppose if it is motor, it will rotate anti-clockwise, no? Like
yes,
this.
sir.
Now, whenever it is rotating anti-clockwise, every conductor of armature will enter at this pole tip. Then what is this pole tip leading?
Yes, sir.
This pole tip will be leading for motor, and this pole tip will be trailing, because every conductor will leave the north pole from here.
Yes, sir.
That will be trailing. So for motor, trailing and leading will interchange, because motor direction is anti-clockwise. No?
Yes,
generator
sir.
we taken clockwise.
Okay.
What is doubt here?
But from where we are conductor entering into the north pole?
Conductor entering into the north pole at this point only. That is trailing for generator. Same pole tip will become leading for motor, because enters wherever it enters, that is lead. Wherever it leaves, that is trailing. So anti-clockwise direction motor rotates. Then trailing will become leading for motor.
Okay. Means for the leading, that is leaving.
Yes, yes.
And for the trailing, it is the entering.
Just opposite. Generator trailing pole tip is motor leading pole tip it is.
Okay.
And sir, what about the flux, sir?
Which
Flux is in generator and motor both side. Where is more?
generator and motor?
Sir, the flux is more only at in generator and in the motor also. At trailing current, flux is more only.
The same figure, generator or motor, figure is same, no change. But motor will rotate anti-clockwise. Only direction of rotation will change. Remaining figures, everything same.
Okay.
Okay.
Okay, sir. Thank you.
Sir,
Tell me.
sir, in this figure, at trailing pole tip, we get more flux because of cross magnetization, sir. That is it right, sir? Am I right, sir?
Right.
Sir, and another doubt, you have said that saddle point will never become zero. That saddle wave, that curve, sir. Why that curve getting touched as zero, sir?
Why?
Why that curve part in saddle shape here, armature flux, that curve part, why it?
It is not
sir.
zero because along, if you see actual this figure, previous one, what is armature flux? Actually, it is south pole, it is north pole.
Yes,
Armature
sir.
flux lies along the q axis only.
Yes, sir.
Now, what is the flux along the q axis? Is it zero? Armature flux is zero? Never zero, no?
Okay, sir. Thank you, sir.
So, good night, all of you.